factoring. Please take it away.
Awesome. Yeah, thanks so much for inviting me to give this talk and for having me. It's amazing to be back in Berkeley. For those of you who don't know me, I did my PhD here, which was wonderful. Now I'm a postdoc over at MIT. Yeah, a little bit during my PhD and in particular during my postdoc, I've been kind of getting excited about thinking about kind of on the theory side, how expensive really is quantum factoring. And a quote that I really, really love, which is from this economist from about 150 years ago, is the one I have up here, where he basically picked two numbers that are, maybe each like, I don't know, 10,000 or 100,000 order numbers, and like multiplied them together, and then just published their product and said, I think like this is a secret that will die with me, the two factors of this thing, and no one will ever know it in the future. And today I'm going to be talking about advances in quantum factoring, but I want to emphasize there have also been some big advances in the past 150 years in classical factoring. So I want to just do a little demo where if we just like use SymPy's built-in prime factors function, it takes like longer to import the the prime factors function than it does to factor this number. So yeah, we've certainly made big progress, but yeah, there's also been a lot of progress in quantum factoring as well. And something I kind of want to address right off the bat is this question of like, why should we even work on this, right? Because at some level, as I expect everyone knows, factoring underlies one of the crypto systems that we use all over the place on the internet, and like it seems just like strictly bad for society if we break it, right? Like this like seems like not a good thing. So like, what is the point of trying to make this easier? And I want to argue it's actually super important that we work on this right now. So just to give an idea of kind of like how close we are a little bit, 5 years or so ago, Gideon Akara estimated that we'd probably need like 20 million physical qubits, with some error correction and stuff to factor 2048-bit RSA, which is maybe something we really care about cryptographically. And actually, it's a particularly fun time to give this talk because Craig put out a paper on last Friday, bringing this number all the way down to like less than 1 million physical noisy qubits. So that's obviously a big improvement. And so given that this is kind of like the range of device sizes that we might be thinking about, I could maybe imagine two hypothetical futures that we might live in. So in one future, in a couple of years, we realize that actually 1 million's still too many qubits. Maybe we actually only need like 50,000 qubits. And then in 2032, we build a device with 50,000 qubits. And in the intervening time, we've kind of watched like the experiments inch closer and closer, and everyone kind of like freaked out, but we got ourselves together and we switched to post-quantum crypto, and we feel maybe, I mean, it's still bad, honestly, but but things are like a little bit more okay. But in another future, maybe we get to 2032, this is kind of our best estimate, we build this device, and then like one day someone just posts to the archive, hey, actually, we actually only need 50,000 physical qubits. And then in one day, we go from like, we probably have a few years before we can break RSA to like RSA is broken, right? And so if the question is like, which future do you want to live in? I like certainly want to live in future A, right? So another way of saying it is like, I think right now is actually a really important time to super duper nail down how expensive factoring actually is on quantum computers, because we're getting close enough that we're gonna be able to do it soon, and we need to know when we're gonna hit that point. There's other reasons to work on factoring too. One, which people who have heard me give talks before certainly knows is near and dear to my heart, is that I really think efficiently verifiable proofs of quantumness are exciting. And in particular, I think it would be really cool if there's some classical questions you can ask some untrusted black box quantum computer or allegedly quantum computer, and based on the answers that you get back, be convinced that it's actually doing something quantum. Factoring is like a great way to do this in that you just multiply some integers together, just like the economists did 150 years ago, and say like, what are their factors? And then I'm kind of convinced if it's sufficiently hard classically that that they've done something quantum. Obviously, the reason that we haven't done this so far is because actually running factoring circuits seems to be a lot harder than other circuits we might run that seem classically hard. But I'm actually going to argue, hopefully by the end of this talk, that certain factoring problems may actually be a really good and maybe the first way we might feel good about doing this. Another reason, which either is very important or not important at all, depending on how you look at it, that I work on this is that I think that the math is really fun. Okay. So there's a question when we're thinking about, like what are the first, say like factoring or proof of quantumness circuits that we're gonna run, which is like, what should we actually be optimizing for in these circuits if we're saying, like when are we gonna hit the point where we can run these things? And if you asked a younger version of me back in 2019, this is me as a young Berkeley grad student, I would have said, my goal is that we can make some proof of quantumness circuit that's so efficient we can just forget about error correction and just like run something on physical qubits, and then we can check the output and like hopefully be able to verify efficiently that the thing that we have is quantum. Now I'm arguably slightly more mature postdoc, and I've kind of gotten convinced that like, well, first of all, I will say that there's probably some clever stuff that we haven't figured out that we can do to do this. For example, maybe we can do things with peak quantum circuits or things like that. But like, if we want to do something based on cryptography, I kind of have started to feel pretty convinced that we're going to need to use error-corrected circuits to do any non-trivial cryptography. And now the question is kind of like, how big do those error-corrected circuits have to be, right? So under the assumption we're working under error correction, we can acknowledge this fact, which is that like the logical error rate goes exponentially with the code distance if we're past the threshold, right? So that's just like a fact of error correction. So if we have two algorithms, algorithm B uses half as many qubits, but it uses 10 times as many gates. You might ask the question like, which of these should we go for, for trying to do this sort of thing? And even though the gate count is way worse, I would actually argue that we want to use algorithm B. And the reason is that if we have some set number of physical qubits with some particular noise rate, if we're using half as many logical qubits, that means we can double the code distance, or I mean, depending on what kind of code we use, I guess we should say double the number of physical qubits that we use for each logical qubit. But since things go exponentially, if we double the number of physical qubits we're using for each logical qubit, we'll get like an exponential decrease in the error rate, which means we can run much, much larger circuits, right? So the take that I want to leave you with, which I've been calling a hot take, but it seems like people broadly agree with it, so it's like maybe a lukewarm take, is that right now what we should like really be caring about in terms of the first things that we're going to run is really actually the logical qubit count. And obviously we don't want our gate count and depth to be like totally insane, but like assuming that those things aren't totally insane, maybe we should focus on the logical qubit count. I'm not saying we should never care about gate count and depth. So that was just concerned with what are the first things we're going to run. As we get kind of bigger and bigger machines, so this, I guess to go back just a little bit, this circuit that Craig has that was just put out on Friday, his estimate is that it'll take like a week or so to run. And so if we're not just concerned about like what is the first time we're going to run one of these things, but like actually trying to do it in practice, if we have a big enough machine that we can handle a larger number of logical qubits, then we really should start caring about depth, because we maybe really care about wall time, right? If we want to do like a bunch of big computations, we don't want to have to spend a week using our quantum computer for each of them. And sometimes we may also want to care about gate count. One time I claim that we might want to do that is if we end up in an error correction situation where we're limited by the amount of magic that we can produce, then like parallelizing the gates in our circuits doesn't really matter that much, because we can't even execute things in parallel because we aren't producing magic fast enough to be able to perform these gates. So if we end up in that sort of an error-corrected situation, maybe we care about actually gate count more than depth. Okay, so yeah, so maybe these are two reasons we shouldn't totally forget about gate count and depth. So yeah, I was planning on, I mean, the way I wrote the abstract, I was going to kind of like really focus on one of the results that, or a couple of the results that I've put out recently, but I realized there's just like so much that's happened in quantum factoring recently that it probably is like a good idea to just give a little bit of an overview for a solid chunk of the beginning of the talk of some of the things that have happened. I want to emphasize this won't be, I guess, totally extensive overview. Like I'm not even going to mention some of the results that have been really big recently, but I'll kind of give a bit of an idea of different things that have progressed in different ways in a way that hopefully helps people understand like sort of where we're going. So, okay, so broadly, what are we doing when we do quantum factoring, right? So all, I guess, polytime quantum factoring algorithms, but probably, we should kind of think all the quantum factoring algorithms that we're going to run anytime soon, rely on period finding, right? So first thing we're going to do while we're at our whiteboard is like find some function which has some period, which we can call t, where the period of that function is useful for finding the factors of our integer n that we're handed, right? Then we're going to go over to our quantum computer. We're going to take some superposition over inputs in the domain of this function. And we're going to generate an entangled superposition where we put the value of the function in the second register. This is kind of a pictorial representation of that, where the color corresponds to the value of f. Then, conceptually, we'll say that we measure this the second register, which will give us some superposition that's periodic with the period of f. And then we'll do a Fourier transform because the period of this thing is t. The Q of t will give us something that allows us to post-process and find the period. And since the period gives us the factors, this is how we're going to factor our numbers. I kind of introduced this talk talking about the costs of things. So I kind of want to analyze before we even specify anything further about what we're doing, what the costs look like. So let's look at the qubit cost. There's like 3 different places we might use qubits. First of all, we have to use some qubits to store this input. We also need to use some qubits to store this output, and then we probably need some workspace in order to compute that function f of x. So, and then the gate and depth cost, essentially, we can essentially forget about everything other than computing this function. That is like by far going to be the bottleneck. So for these 3 things, what are each of them going to look like? So for the input, our goal is to do a Fourier transform and find something, find the period which looks like t. And a nice analogy that I think is kind of fun that I like to use for this is I've been learning a little bit how to play the upright bass. And something that's good when you're learning how to play the upright bass is that the frequencies are low enough that if you play quickly, no one can really tell if you're out of tune. And and so the relevance here, right, is that we need our function to wrap around our period some solid number of times so that when we do the Fourier transform, we're actually going to get a good frequency out, okay? And what this means is that for a particular period t, we're going to need something that looks like log of t qubits for our input register so that we can have that thing that wraps around enough times. Okay, for the output, well, if we want to have kind of a unique value for each, I guess for each representative of each coset, it seems like we're also going to need log t qubits here, right? Because we need something that can uniquely identify each of these things. And then for workspace and the cost of this thing, it's kind of just well, you define what your function is, then we figure out how expensive it was. Okay, so these are kind of, I gave some sort of hand-wavy arguments why we might need this. What I'm actually going to say next is that when we're trying to reduce the qubit cost, there's actually some surprising tricks we can do to not be limited by these seemingly fundamental barriers. So yeah, I guess before I jump into what we're going to actually do there, I just want to actually instantiate this, right? So what Shor presented in his factoring algorithm 30 years ago is that for this function f of x, we should pick some classical value a and compute a to the x mod n for the inputs x. It turns out the period of this will be if you're a number theorist, it's the order of a in the multiplicative group mod n, but the kind of intuitive idea that you should have is that this period is going to look something it's going to be of roughly the same size as n, okay? It's going to be big, kind of that order. And if little n is kind of the length of this number big N in bits, we can kind of actually give numbers to these things. So maybe this input x is going to be something like 2n qubits because we need to wrap around some good number of times. The output is going to be something that looks like maybe n qubits. And then the workspace, again, depends on how we implement a to the x mod n. Okay, so let's start reducing these qubit costs. So the first idea to reduce these qubit costs actually has to do with this input register. And this was an idea that was already presented way back in 1998, just a couple of years after Shor introduced this algorithm. And so the key observation is the following. If we want to do a modular exponentiation like this, well, we can rewrite it as just the product, the conditional product of some classically computable constant ci, where we include a particular constant in the product if the corresponding bit of x is 1, and we don't include it if it's 0. And these constants are just like a to the 2 to the I mod n for each I. Okay, why is this helpful? It's not clear how this has already reduced the number of qubits. Well, the key thing is that given the structure of the quantum Fourier transform and the fact that we're gonna measure it immediately afterward, this kind of says that like each bit can talk to this product individually, right? So we don't have to kind of like reuse the bits multiple times. All we have to do is like condition on a bit, multiply it in, and then it turns out, due to the structure of the QFT, we can just do that once, measure the qubit, and then put it in uniform superposition again, do it for the next constant CI, and just do this over and over. The result is that this input register, we're actually just going to need to use a single qubit, which we use over and over and measuring with each iteration. We're still going to have this like n qubits in the output register, and then the cost is going to just have to do with doing all these multiplications. And in terms of these multiplications that we have to do, it just looks like this kind of controlled operation where we have a single bit, and then we have some accumulator register where we've been accumulating the product, and we multiply in CI conditionally on X. Okay, cool. So that is something that's been known since 1998. And some results I'm actually going to present later in this talk are essentially just a really fast way of doing this operation. So inside of this structure, we can do this super efficiently and overall make the circuit for Shor's algorithm really small. And I guess that's a continuation. The idea I want to convey is that's a continuation of work that's been happening. Like, there was a flurry of work after Shor first published his algorithm, and this idea came into prominence of how to implement this thing really fast. Okay? But fundamentally, we were kind of always stuck with like, this size of the output register, and then some non-trivial amount of workspace for the multiplication, and also some linear number of multiplications for the cost. And I guess something I'll mention is that 2019 paper that did this estimate. This is kind of what I mean by like, this is kind of what we've been doing for the past 30 years. Aside from some small tweaks that get this down to n/2 instead of 2n, this is broadly the structure of the algorithm that was used in this 2019 estimate, getting 20 million physical qubits to do this. Okay, so what if we do something different? And instead of trying to get this input register down to 1 qubit, we're actually going to try to get the output register down to 1 qubit. Okay, so what I mean by that is, for our period finding, this fn of x is no longer going to be a function that goes to some long bit string. It's just going to be a function that goes to a single bit. Okay? So for our period finding, we're going to do the same thing, but as you might notice, now there's not like a bunch of colors here. There's just 2 colors, because we're just going to get a 0 or a 1 for each bit of this thing. We're going to do the same thing, though, where we generate some superposition over these x's and then evaluate the function. When we measure this thing, or don't, but let's just say we measure it, I guess this is a slight typo. We won't get a superposition over a coset. We'll get a superposition over a bunch of cosets, right? And hopefully, if we do a QFT now, because like it's a superposition of a bunch of things that are all periodic, we'll still get some reasonable period out. There's some questions you might ask about this, especially considering that like 5 years ago or 6 years ago, I guess, in 2019, this strategy was not used, which is like, is this going to actually help, or even will it work in the first place? So let's look at some problems that might happen with this. First of all, there might be some period smaller than t, right? We're not like getting a single coset. We're getting some superposition of cosets, and which superposition we get depends on what this function is. So if we just like do a QFT on this, depending on the structure of this thing, we might not actually get the period that we wanted out. We might get some smaller period that has to do with what superposition of things we got. And there's actually, way back in 2000, Hales and Hallgren did some analysis of like what happens if you do period finding on something where the outputs don't uniquely identify the cosets, but it wasn't really clear what to do with that in terms of factoring. Another thing that we're still running into, right, is like, we used this trick earlier that allowed us to use just a single qubit for this input register, and this idea kind of like kills that trick. It turns out if you want to do this, you're going to just end up having to take a full like superposition of all of the qubits that you need in this input register. And we said that for Shor's algorithm, we're going to need like 2n qubits for that. So it seems like we're not even winning on qubits. Yeah.
So going back to the trick where you do 1 qubit for the input,
yeah.
How do you then do like a Fourier transform?
Good. So the idea is like, you do this thing called a semi-classical quantum Fourier transform, where you're actually kind of doing the quantum Fourier transform as you go along. So like, you set this one qubit, do the thing, and then if you look at the structure of the quantum Fourier transform, like starting at the least significant bit, you're actually just going to do a Hadamard gate and then measure, and then you're going to do a bunch of kind of like controlled rotations based on the Hadamard qubit. Well, what you should do is just do the Hadamard measure and then do a classical control. So you just do this over and over, basically. You just keep measuring it, and you're like doing the quantum Fourier transform as you go along. Yeah, so, but unfortunately, we can't use that trick anymore if we're going to do this thing. I mean, if we could, it would actually be perhaps catastrophic, because like then you would use one qubit for the input and one qubit for the output, and then you'd have a 2-qubit factoring algorithm, which seems like probably probably not real. But I guess another thing that we have to worry about, right, is like even if the output is really small, we need some number of qubits to actually compute the value. And if we use like some big number of qubits to compute the value, then why did we even compress the value down to 1 bit if we used all the space to compute it in the first place? So for Shor's algorithm, there have been kind of like various papers that have chipped away at each of these problems. And I'm going to walk through them right now. So this paper, from 2022, showed that, okay, if what we're worried about is, having this superposition have some smaller periods than t, which we wanted, maybe we can just take some hash function, which looks kind of random, and just apply it to a to the x mod n. And then this feels kind of good, because if this thing is random, it's unlikely to have some structure that will give us some extra periods, and we're probably going to do okay. There's some maybe clear problems with this, is like, can you compute just the hash of a to the x mod n without actually computing a to the x mod n in the first place? Because if you can compute a to the x mod n, you might as well have just measured that. Why did you do this hash thing? Also, we still have this problem with the input register having a bunch of qubits, and we're still doing a bunch of multiplications. So regarding the input register having a bunch of qubits, there was a really nice paper that actually came before this one, showing that instead of using the normal a to the x mod n to factor a number that looks like n equals pq, we can actually cast it as a short discrete log. And in particular, the discrete log we're going to compute, we can do something which has a period that looks like square root of n, which means that, and they also show that we don't actually have to go too many cycles around our period. So it turns out you actually only need n over 2 plus a few qubits for the input register using this trick, which is pretty cool. And then if we apply this hash thing, we still only need 1 qubit for the output. But again, we haven't really established how are we actually going to compute that 1 bit without computing the entire n-bit thing. So maybe we need some n qubits still for workspace. But this is like progress, right? We got the input smaller. And then in a really, really cool paper last year, Clément Chevignard and co-authors showed that there's actually a really cool trick you can do using residue number systems to use just like sort of in a hand-wavy way, like log space for our workspace rather than some linear space. So this is like getting pretty serious now, right? Because we've managed to get the input size down to just n over 2 qubits. We're just using 1 qubit for the output, and now we're just using some log space for the workspace. Yeah.
So isn't like the whole point of a hash function that if I change some small number of the inputs into it, it should totally change the hash?
So this is true. Sorry, I think I don't follow why.
So it would seem like you would have to handle all of the qubits.
Oh, okay, good. So, okay, I've slightly hand-waved something under the rug here, which is that they don't compute something that looks like a normal hash function. They actually show, or I guess conjecture, but it seems reasonable, that you don't really need to compute a hash function. You can actually just look at the low bit of a to the x mod n.
So you're not really...
Yeah, you're not really computing a hash function, but they say we can just use this much workspace, only compute the low bit of a to the x mod n, and then we're actually happy. That's a good catch. The challenge with this paper, right, is we've actually done an amazing job on the qubit cost, but like the gate cost is quite large. So in their estimate in their paper, it looked like it take maybe like 2 trillion Toffoli gates. And even with what I said earlier about we should care a lot more about qubits than depth, this is like a lot, right? So it's like, okay, this is really cool progress, but like maybe we shouldn't just run this circuit out of the box. And in the paper that Craig put out on Friday, he essentially showed that if we do a bunch of optimizations to the arithmetic and also do a bunch of really clever fault tolerant stuff, we can just like do way better on this Toffoli count and also how to implement it. And that's how we get this factoring in less than a million physical qubits. And it'll take maybe a week. Something I'll note actually is that this week is actually longer than the 8 hours that were claimed in the 2019 paper, and this is kind of an instantiation of this claim that like maybe like the depth and the gate cost are not what's super duper important. What's really important for making things work on near-term devices is the logical qubit count. Okay, cool. So that is some stuff that I did not work on. That yeah.
Sorry, quick question. Like,
Yeah.
1 week is like one quantum circuit is running for a week, or you run.
So indeed, well, okay, sorry, not exactly. You do take several shots, but I think you take like 10 shots or something. So yeah, so the quantum circuits I think are running for like, yeah, I guess a week over 10. Yeah, but also I think this just is related to this idea that like once you're past threshold, you can just kind of like push the codistance and then you actually can get really, really low error rates. Okay, so at this point, I want to transition into talking about some things inside of this framework that I've worked on. So the first is kind of in this second regime where we try to like somehow compress the output onto 1 bit and then see what we can do to make things more efficient. With some co-authors, I have, we have this work where we show that you can actually, for integers of a particular form, get a factoring algorithm that uses sublinear space and depth. And just, yeah, for comparison, in the previous slides, we managed to get down to like little n over 2 qubits. Here, we're actually going to get to sublinear. So not just some constant factor, better than little n. We're going to do even better than that. A paper that we just put out a few weeks ago is this really low depth quantum Fourier transform, which doesn't use ancillas, but also is like catastrophically wrong some of the time. So it has this weird model of the error where usually the error is small for most inputs, but there's some part of the Hilbert space where the error is like really big. And I'll talk about that a little bit. And it turns out if you combine this with a paper I've talked about at Simons before, where we can do certain phase rotations super fast, this gives us a multiplier that is really low depth and also doesn't use very many qubits. If we plug it into the first construction where we're making the input register small, it gives us an implementation of Shor's algorithm, which is just over linear depth asymptotically, and also uses just a little bit more than 2n total qubits. So I'll say this result is more targeting kind of this like near-term thing where we're really constrained on qubits and we want to do everything we can to fit things in as few qubits as possible. And this result is more in the long term where maybe we care about like wall clock time or something like that. And we want to be able to factor numbers in as low depth as possible or as low space-time volume as possible.
Couple questions.
Yeah.
So could you compare this to Regev's algorithm?
Yeah, sure.
What's better and what's worse?
Sure, certainly. So yeah, I guess I notably didn't talk about Regev's algorithm yet. So the thing with Regev's algorithm is, at least as it currently stands, it seems that it is not known how to apply the same tricks that like Chevignard used to get the qubit count really small. So it seems that if we want to use Regev's algorithm, we're going to be stuck. I mean, I think the current best is from Seon Raghavan and Vinod Vaikunthanathan, which is, I think, like it's like 11 times little n number of qubits or something like that, which is like, just considerably bigger than all of these things, I guess. Yeah. On the other hand, the depth and the gate count of the circuits that you run under Regev is really small. Given what I talked about at the beginning, it's not totally clear if that's what's important for the first, instantiations of these things. On the other hand, once we have big machines, maybe that would be a good thing to do if you really, really care about the wall clock time. But I guess you'd have to be in a situation where you have like a bunch of parallel quantum computers that can do shots individually.
Right.
And then you kind of like classically post-process all those shots you did individually after. So
I see.
Yeah.
I see. And also, so it's like something really weird and special must be happening with these n equals p squared q.
Yes.
To get that kind of reduction. I mean, could it be even better with if n equals p cubed q?
Ah, good. So I'll show you. I can just jump to it right now. I'll show you more kind of in a more precise way what these complexities look like. So yeah, first I'll just say, this is a work that I worked on with my wonderful colleagues Seon, Vinod, and Catherine. So yeah, to go a little bit more in depth about the complexities we have here, in particular, the complexity is going to be proportional to the length of Q in bits, okay? And this is kind of neat because like in the classical world, we have factoring algorithms whose cost depends on the size of a factor rather than the size of the whole thing. And this is like not really a thing that we had in the quantum world. So it's kind of neat that for these particular numbers, we have something like this now. And in particular, the space requirement, whether we use kind of like simple circuits or we use fast multiplication circuits, the space is going to just be proportional. It's only going to care about the size of this Q. It's not going to care about actually the size of n at all, which is nice if we want to do something like a proof of quantumness, because we can kind of like set Q to be whatever we want, right? Like this is something we can tune and we can make reasonable. So I guess to answer your question, like kind of no matter what the form of this number is, the cost of this thing is going to just care about sort of I guess to be precise, it's going to care about the size of the square free part of the number. Yeah. Okay, so if we have these complexities, and we want to do, say, a proof of quantumness, what should we set m to, right? Like how big should we make Q? Because if we make Q too small, then the whole thing is going to be easy to do classically, right? But we want to make it as small as possible. Well, just looking asymptotically, we have various classical factoring algorithms. Maybe, the general number field sieve costs something that looks like an exponential in the cube root of n. Lenstra looks like the square root of the length of this factor. So if we kind of set these equal to each other, we probably want to hit some kind of like corner, which is the length of Q is like the length of n to the 2/3. Okay, so it's like kind of what we should aim for if we want it to be as hard as factoring RSA, but we want it to be as easy for the quantum computer as possible. And if we plug that in, then these are the complexities that we get for this algorithm. So I want to jump into how we actually do this. Are there any questions before I do so? Yeah.
I gained some intuition on constants versus asymptotics here. Like for example,
Sure.
Statements I heard was right, trading space for depth often doesn't make sense because it's much cheaper from the qubit perspective given the exponential error correction, right? When we look at these gate depth trade-offs, right, there's a similar question of, well, is it actually worth it from a constant factor? Maybe that trade-off point is
Indeed.
So I guess like what's the state of the art? Like how well have we costed this? Have we started factoring and mapping, routing considerations, things like that?
Yeah, indeed. So this is a pretty new result that in the paper that we published, we only kind of did asymptotics. But I guess I'll just say, as someone who has spent maybe more of my life than I than maybe was appropriate, trying to compile circuits like this into like concrete things, I'll just say that like the constant factors on these things actually feel quite good. Like it feels nice and hope
like an algorithmic improvement rather than more like you're doing a lot of contrived work in order to kind of get this asymptotic.
Yeah, in particular, like these using just kind of like straightforward multiplication, et cetera, algorithms, like the costs and the constant factors feel quite nice. If we want to literally get these things, we don't want to actually use fast multiplication algorithms in practice, aside from maybe some that I'll talk about later in the talk, actually, which maybe actually are kind of reasonable. Okay, cool. So how do we actually do this? Remember what we had earlier where we had this idea, maybe if we kind of make this function just map onto a single bit instead of mapping onto a bunch of bits, we can get some wins. But the things we had to deal with in the case of Shor's algorithm were a few things. First of all, we needed the period to be small, because if the period's too big, we're going to need some really big superposition over these inputs, so we're not actually going to win. We also need to be careful that the function that we doesn't have smaller periods than the one that we care about, this period t, right? Because that'll break us, and we won't actually be getting t out anymore. And we also don't want to use that much workspace to compute this function. So how do we go about even finding such a function, right, that we might want to use in this case? Well, if you're me, how you go about it is you just sit in your office, and then one day your brilliant grad student colleague, Seon, walks into the room and says, I found a function that has a really small period. So let me show you what Seon told me about that day. And it starts with some number theory. So there's this idea called the Legendre symbol, which says that if we're looking at a particular number x mod p, the Legendre symbol is going to take on the value 0 if x is 0 mod p. It's going to take on 1 if x is a quadratic residue mod p, which just means that there is some number that squares to x. And it's going to be -1 otherwise, okay? So it's not clear what the motivation is yet for this, but this is like something that you can write down that people care about. Something that's neat about this is that it's efficient to compute if you know x and p, and it's also, of course, periodic with period p because it only cares about what the number is mod p. So clearly it's going to be periodic mod p. There's a generalization of the Legendre symbol, which is called the Jacobi symbol, which essentially says for any composite number n, we can just actually take the product of the Legendre symbol with each of the prime factors of n, and then define something called the Jacobi symbol. Again, the Jacobi symbol is efficient to compute if you know x and n. But we might say, what is actually the period of this thing? So let's take a number n equals pq, like we care about with RSA. This thing is going to be the product of the Legendre symbols mod p, the Legendre symbol mod q. If we kind of ignore the cases in which this Legendre symbol is 0, because that only happens very, very rarely if p and q are big, this thing is going to look kind of like it's periodic with period n. This is not helpful for factoring, right? Because if we do period finding on this, we're just going to get n back. And if we're trying to factor n, getting n in a really convoluted way is not useful. But if our number that we're factoring has the form p squared q, this is actually pretty cool. Because remember, this thing is, for all intents and purposes, just going to take on the values +1 and -1. So the Legendre symbol of x mod p squared is always going to be +1, right? So this thing we can just kind of drop, and then the Jacobi symbol of x mod n is essentially going to be the same as the Jacobi symbol of x mod q, which is really nice because this thing is periodic with period q. Okay. So this is actually kind of neat. It's like, unlike in Shor's algorithm, you don't even have to do, well, you have to do a little bit of post-processing, but once you get the period, you don't really have to do anything to get the factors out. You don't have to do some like clever number theory math. You just like, the period is one of the factors. So that's pretty cool. Okay, so we have a small period t, which is kind of what I alluded to earlier, right? Is that like this thing is gonna cost something proportional to the size of this factor q. We want to know if it avoids these smaller periods, though, right? Again, we're only mapping onto single bits, and there's some question that maybe if we measure this thing, we're going to get something that could have some smaller periods. I guess it should be said that like if q is a prime number, there's like nothing that divides it, so we like can't exactly get any smaller periods. But there's actually still something to be said for like, it turns out what you really care about is if the function's even anywhere close to having something that has a smaller period. So there's like maybe still some issue we could have there. And so let's ask this question, like if we take the Fourier transform of the Jacobi symbol, what do we get, and are we going to get something that's useful out? And one might ask, like, this is like kind of sounds like an annoying thing to compute. I wonder if anyone's ever done this before. So you look in the literature, like maybe a lot of people in the past few years have done all kinds of math. So maybe someone has done it. Turns out we actually get helped out by Gauss in the early 1800s. And there's actually this kind of miraculous feeling thing where not only are you not going to run into this problem where you kind of like concentrate onto these smaller periods that will cause a problem for you, Gauss actually showed that like this thing has somehow the ideal Fourier spectrum where it'll actually kill any of these like problematic periods, and you'll like actually kind of always get something that's useful. So it's like not even like in the random case where we say, oh, we have some like random hash function, it'll probably be fine. Here it's like somehow like actually the universe has conspired to give us something really, really useful that will like actually always give us something correct. So that's pretty cool. So far we have a small period t, and also we're doing a really good job avoiding these smaller periods. And it turns out this was actually known in the literature in a paper that like seems to have been like surprisingly not super well known by the community. So back in 2012, people made this observation and they said, hey, like this is pretty cool. We can actually use this Jacobi symbol to factor numbers of this form. And in particular, they said, well, might want to use just kind of like standard, we have classical circuits for computing the Jacobi symbol. Maybe people have some like related quantum circuits. We can do that using some linear amount of space. And I guess the main claim of this paper was, this kind of nice thing about these Gauss sums that I mentioned on previous slides, which is that if you actually do the quantum Fourier transform mod n, you're going to have like a 100% certainty successful factoring algorithm, which is pretty cool because this isn't true for Shor's algorithm, right? With Shor's algorithm, there's like some chance that things might go wrong and you might have to run a few times. Here, if you do the QFT mod n, you just always get the right answer. You always factor with a noiseless quantum machine, which is pretty cool. But for our purposes, right, we're talking about like reducing the space and stuff like that. Kind of like this is what kind of kills us, right? Like if we care about the space, we're like not actually doing that much better than just running Shor's algorithm on something like this. So one can actually think of our contributions kind of similarly to the thing that like Chevignard did in showing like maybe we can actually really reduce the workspace to compute these like single bit functions to do a lot better doing period finding like this. So our first claim is that there's actually extremely efficient circuits that allow us to compute the Jacobi symbol using much less than a linear amount of space in the size of n. And then the other thing is just to say, hey, we don't need to take this superposition huge like they were taking in the original paper. Maybe we can just take it up to some, like x goes up to like q to the 1 plus epsilon or something, and then we'll still get decent periods out. Okay, so how are we going to do that? In particular, how are we going to do this first bullet point? So we want to compute the Jacobi symbol, which, as I mentioned earlier, will take on values either -1, 0, or 1. Something that's kind of neat when you have these functions that just have like a single bit output is you don't even need to put in another register. You can actually just apply it as a phase onto your superposition, and then it actually helps even further with the success rate of your algorithm. And the key observation here is that we have two inputs, one of which is potentially much smaller than the other. So the quantum input is only m qubits, and the classical input is n classical bits. So maybe we can actually do a lot better than using some little n number of qubits. Can we actually implement the circuit just using sort of like some number of qubits that's linear in the smaller input? And the idea is yes, and I'm not going to go, or the answer is yes. I'm not going to go deeply into how we actually do this, but I want to give you the intuition. And the intuition is that since n is a classical number, we can actually kind of like stream through its bits. Like we don't have to give the entire input n into our quantum circuit at the same time. We're just going to give it little chunks. And in particular, kind of the crux of our algorithm for doing this is to observe, okay, we have some big classical number n, we have some small quantum number x, and what we're going to do is kind of like build up this number n prime, which has a Jacobi symbol with x that's related to the Jacobi symbol of x and n, okay? In particular, what we can do is we can actually like split off some like order m size chunk. It'll actually be 2m of the classical bits of n. And then we have a transformation which computes some n prime where in our quantum system we have some, something that we're holding in our qubits, which is some, little m number of bits, and then it turns out a bunch of things that all end up being 0. And then the top of this number is all still going to be classical values, okay? So the idea is the only thing we actually have to hold in our quantum computer is this. In particular, once we know these things are zeros, we actually just have a bunch of qubits again that we can work with, so we can kind of like use them again in the future. And I guess another important feature of the Jacobi symbol is that if we know that a number ends in a bunch of zeros, there's actually a way we can easily just like right shift that number and get rid of those zeros. So now we notice this thing has gotten smaller. So now we just do the same trick again. We peel off some chunk of bits of this classical number n. We do the same thing. The bottom's all zeros. We scoot it over. We can just keep doing this like eating through these bits of the classical value n until we've streamed through all the bits. And now we just have two quantum values which have a Jacobi symbol relative to each other that's related to the Jacobi symbol of x and n. But the nice thing is these are both this little m bits long. These are both really short numbers. So now when we've gotten to this point, we can just use like some standard circuits to compute the Jacobi symbol, and we'll get something that has both depth and qubits proportional to the size of this little number m, okay? So just to like go back out to the big picture, what we've done is found some function specifically for these numbers of the form p squared q, where we get all the three things that we needed for this weird type of factoring where we only have a single bit for our functions f. We got the small period. We avoided having any weird pathological interference between the cosets that we measure, and also we figured out a way to use low workspace to compute this thing. So just to flash back up our complexities, again, this is what they look like. To answer the question a little bit that was asked earlier, this is extremely hand wavy, but from playing around with things, it seems like space that's just like 2m probably is achievable. So so not a huge constant factor there. How many bits is classically hard is unfortunately a pretty annoying question to answer. So one can look at like the cost of, for example, factoring numbers with a small factor, and Lenstra starts to run out of steam around maybe like 300-bit factors q. On the other hand, there's this other algorithm specifically for numbers of this form, which has the same scaling in the exponent, but has a better constant factor. And since it's a better constant factor in the exponent, that's like, you should care about it, right? You can't just like ignore this constant factor. But as far as I know, there's no like super optimized implementation of this classical algorithm. So how many bits you need here to be classically hard is kind of dependent on like, if someone were to build like a super highly optimized implementation of this, how far we should push it. But I think, worst case, it certainly, shouldn't get better than, or get worse than like 500 or 600. And hopefully we can, run a classically hard factoring circuit with, less than 1,000 qubits or so.
Wait, so somehow we went from 1 million to 1,000?
Oh, sorry, this is logical qubits.
Yeah. Oh, okay.
Yeah.
So let's say let's call it five a few hundred to 1,000 logical qubits compared to for the Shor's algorithm for an arbitrary n equals p times q.
Yep.
What would be the estimate there? Like how many times greater would that be?
Good. So the number of logical qubits in the implementation that Craig used for this estimate was like 1,500 or so.
Okay.
So we're doing maybe like a factor of 2 or so better in terms of logical qubits. It's also worth noting that the actual size of this circuit, something that I think is cool about this is like Craig was taking a hit on circuit depth in order to achieve this really small thing.
Right.
Here we're actually doing super well on depth also. So presumably, I mean, because of this exponential, you never win by that much, but presumably you can make your codistances smaller and things like that to be able to like fit it because you're doing such a smaller circuit.
So just to check, are you saying, why is this a classically hard problem?
Oh, just because factoring this type of number, if q isn't too small,
Isn't it just compute the Jacobi symbol? Like, isn't that a very efficient thing to do? And doesn't the Jacobi symbol just give you q?
So the Jacobi symbol doesn't give you q. The Jacobi symbol is periodic in q. So just computing the Jacobi symbol, classically, it's not clear what to do with the output in order to figure out q.
Okay. But it remains to do the full constant factor analysis for this proposal, analogous to what Craig did.
Exactly, yeah. But hopefully, all the really beautiful and incredible compilation tricks that Craig did will carry over without too much hassle. It's obviously it's more complicated than just saying, Craig did cool stuff, let's just do the same thing here. There's like a lot that's specific to the algorithm that was being run, but like it seems not crazy that one could do similar things.
So there are also these proofs of quantumness that are more like interactive.
Yeah.
So what is the lowest number of qubits for those to be?
Good. Yeah, this was all of grad school for me. So the thing is, yeah, I worked a lot on such proofs of quantumness. One of my favorites is based on evaluating the function x squared mod n for numbers n equals pq. This is really cool because you can actually get like crazy low depth circuits for this and not using very many gates. The problem is that the space is still going to be proportional to the length of n. So like, and it seems like you just can't really get around that. I mean, I've certainly tried. So I think the takeaway there is like the circuits are really, really small for doing these x squared mod n proofs of quantumness, but the space you just like kind of get killed. And since what we were saying is if we want to do, a proof of quantumness in the near term, the space is probably what's important. It seems like not totally ideal.
So how do you have a sort of the number of logical qubits?
Yeah, for that, you're in the same range as what Craig was doing. So you can get away with like 1,500 or so,
So
maybe.
that's confusing that this is beating the best interactive proof of quantumness. This is also it's strictly.
Yeah, indeed. So this is, I agree. So one way of looking at it is like, I was also surprised, after spending many years of my life trying to make really good interactive proofs of quantumness.
Should be strictly easier.
Yeah, then there's this algorithm, which is like, seems just kind of better. And I should say, there's other functions than x squared mod n you can use in the interactive proofs of quantumness, but they either use more qubits or have a huge gate count, or they use both more qubits and have a huge gate count. It's just like doesn't seem like
Does
there's.
this make you hopeful that there could be an interactive proof of quantumness with like 200 logical qubits?
That would be really cool. That's also something I was searching for like years in grad school and never figured out. So I certainly think it's plausible, but I don't know how to get there. Okay, so I have like maybe 10 minutes left. So I guess more questions?
Do you think there's space for windowed arithmetic in your circuit and more general space-time trade-off?
Good. So this circuit actually, wait, let me think for a second. I think we decided that there is a nice way of doing windowed arithmetic, although I have to think about it for a second. The challenge with windowed arithmetic is that windowed arithmetic is really nice if you're kind of like adding or multiplying classical numbers by quantum values right here. And here, I think you're mostly gonna end up doing like quantum multiplications or quantum addition. So I think you get a little stuck. But if I remember it, I think there was a clever way that we said, well, you can like kind of do windowing, So there is room to do clever things like that. Although, yeah, something that's I think interesting is that like, so as is kind of implied by this slide, we're doing multiplications inside of this algorithm, but they're multiplications of size m. So like fast multiplication stuff, like I'm actually going to say next, is like less useful than it is if you're working with Shor's algorithm with 2048-bit inputs, just because the numbers are small enough. Like you don't win as much from the asymptotic scaling. So there's I actually kind of have been leaning towards like maybe we should just do the school book thing. Like maybe these kind of other optimizations don't actually matter that much. Yeah.
Does the algorithm work for all n? Like it can find the square root part of n? Or
Yeah.
It needs PQ to be prime or not?
No, it doesn't need them to be prime. So yeah, if in the paper we actually discuss, you can use this just to do a square-free decomposition. And actually, in fact, if you just have any n in which the exponents on the prime factors are unique or like distinct, you can actually fully factor that thing by kind of just like peeling off prime factors by doing square-free decompositions. Cool. Okay, in my last 7 minutes, I just want to talk about this other result that also is relevant to factoring that came out recently, just because it's kind of fun. To motivate this a little bit, I actually have given a talk here before about how to do fast multiplication on quantum computers. In particular, I focused on if we want to implement a unitary that looks like this, so parametrized by some classical value A, we want to multiply it against some input that's quantum. Draper in 2000 proposed that we could do this via the quantum Fourier transform. So if we look at the QFT of this output register, it's just going to be a uniform superposition whose phases are proportional to the product that we want to compute, which suggests to us a way maybe of computing such a thing, which is that first we put this output register in a uniform superposition, and then we apply phases proportional to this thing, and then we apply the inverse QFT. Now, in this previous paper, which I've talked about here before, we showed that you can apply this phase actually rather efficiently. So for any epsilon greater than 0, we can do this in like n to the 1 plus epsilon gates and n to the epsilon depth using only some sublinear number of ancillas. Actually, if you don't care about depth, you can do this in 0 ancillas, but if you want to parallelize things, you need a few. And when I figured this out, I actually thought like, cool, this must just be a fast multiplication algorithm that also has these properties, because there's no way that the QFT is going to be the bottleneck. The QFT is never the bottleneck for anything. I was wrong about that, it turns out. So if you want to get this low in silicount and a sublinear depth, it turns out that there didn't exist a QFT in the literature that could do this. So this ended up turning into this project that was super fun, in which I worked with these wonderful folks, figuring out how to do a QFT in lower depth without the need for ancillas.
Wait, why is QFT the bottleneck now?
Just because we are using a sublinear number of ancillas and we're using sublinear depth, and it turns out achieving both of those at the same time just wasn't known.
I see.
Yeah.
And like if you optimize everything else enough, then the QFT is what's left.
Exactly. And I didn't even realize this had happened. I just optimized this until I was satisfied, and then I was like, oh crap, the QFT is too big. So this is what happens.
I see.
So how are we going to do this? So this is, I guess, what people frequently write down for the QFT. There's also another, way of writing down the QFT, in which we can write it down, it turns out, as the tensor product of a bunch of single qubit states. And in particular, what we're going to have is like these single qubit states that are in a superposition, and the phase has to do with the bits of this input computational basis state X that are like smaller than the index that we're at, okay? So this is kind of like a nice formulation of the QFT, and we can actually rewrite it a little bit. Oh yeah, sorry, something that I should mention is that something neat about this is it gives you a really obvious way to do like an approximate QFT, which is that, this is we can think of it as like a binary fraction. So the importance of these bits gets less and less as we go further and further, and we can just kind of like truncate this after a few, and then we're not really affecting the phases that much, and we get something that's approximately right. Another way we can rewrite this is we can observe, okay, if we don't want to phase on 0 and we want to phase on 1, we can just write that as a superposition of 0 and 1 in which the phase is multiplied by yj, right? Some bit yj, and then the phase will only get applied when yj is 1. But it turns out there's kind of a nice generalization of this. This we can think of as we've expressed it in binary. Instead, we can use some larger base. So maybe we set our base to like 2 to the m and write things as numbers in that base. And if we do that, we'll get actually something that looks pretty much the same, where we have a superposition of all possible yj's in that base. And then the phase is proportional to like the value of yj times some fraction, which is no longer a binary fraction, but a fraction in this new base. And then we have the tensor product over these blocks, which are no longer single qubits, but it's some like m qubit blocks. The nice thing about doing things in this base is that to get this approximate QFT, because we're using a bigger base, we actually always only need to hold like 2 digits of this approximate fraction, okay? This leads to kind of a convenient way of writing down an approximate QFT in the, viewed in this way, where we get, so we're only gonna have 2 terms, as I said, in the phase. The first term we get just by doing a QFT on that block, which gives us, xi times yj. And then we're just going to do some like little phase rotation only touching the next block, which gives us the second term. And this is a good approximate QFT. So looking at it from this structure, what is actually causing us to have this long depth, right? This is kind of sad because like most of the qubits aren't really doing anything, but it's also nice because it doesn't use any ancillas. The reason that we're stuck with linear depth is that like we want to apply some phase rotation to this thing, which is done by these gates. But we can't apply that phase rotation, which is supposed to be proportional to this value, if we've already played with this value, right? So we kind of have to wait until we're totally done setting up this block until we start playing with this block by applying a QFT to it. How are we going to get around this? Well, let's ask a question. What happens if we just apply an inverse QFT on this small block of m qubits to the following state? Well, this is just the QFT of x, so applying the inverse QFT to that gives that. What about this state that I was just talking about, where we've already done this phase rotation? What are we going to get in this case? Well, it turns out this is just equivalent to quantum phase estimation. And what you get is some like superposition that's peaked near the value that your phase was centered on, okay? And remember, our goal was we didn't want to have to wait to start doing this stuff until we've done the previous ones, because we wanted to be able to somehow access that input value xi. And so here feels like we have something promising because now we're getting something that's like peaked around that value xi, okay? There's a subtlety though, which is that when we do this quantum phase estimation, if xi is too close to 0 or 2 to the m, this superposition is actually going to wrap around. And then when we do our phase rotation, some of the superposition is going to give like a wildly wrong phase rotation, right? Because of this tail. Well, I'm right at the end, but I think we can get through the end of this in reasonable time. We're just going to forge ahead with reckless abandon and forget about the fact that there's something wrong here and just see what happens. So the replacement we're going to potentially make is, instead of like this pattern of gates we had in the original QFT, we're going to do this inverse QFT so that we can do this phase rotation after we do these first ones instead of before. If we put this into the circuit, this allows us to shift that whole thing back. And if we have more than 5 blocks, we can kind of keep doing this all the way down. This will end up giving us this kind of cool circuit, which is like a translationally invariant QFT somehow. And it has some cool features. So it only is ever going to have these 5 layers, each of which has depth log n because the size of these blocks is log n. It doesn't use any ancillas. The gates are actually local. Like written like this, the gates have at most logarithmic range. It turns out it's like fairly straightforward to actually get them to just be nearest neighbor for qubits in 1D. And it has the cool feature that it doesn't give the right answer. But the key is that it only doesn't give the right answer sometimes. And like just to look at some numerics, you can see that like this is just some measure of the error for different inputs. It's like the error is exponentially low in the size of this block M, except for a few states. And so the content of our paper is largely like, given that we have a QFT that works on the vast majority of states, but not all of them, what should we do with it? One idea is we can use it anyway. And if our inputs aren't like pathologically concentrated on these bad ones, it should actually be fine. And we show that that works for Shor's algorithm. And the other thing that we can do is do some kind of like worst to average case reduction where we add some circuit on either side that, instead of it working on most states, allows it to work on all states. That's all I have time for, but happy to take questions.
Are there any questions for Greg?
Do you have like a succinct description of what states it fails on?
Yeah, totally. So the key is this issue where like the phase estimation wraps around mod 2 to the m. So if we write down our input state as a bunch of blocks, which are like these values mod 2 to the m, essentially, I mean, in a kind of like informal way, we can say if any of the values is too close to 0 or 2 to the m, then this thing is going to fail. In the paper, we kind of show like we give some explicit bound on like how close you can get and how big the error is going to be.
Is the gate count for your new QFT circuit the same as the old gate count?
It's a little bit more, just because you had to add this inverse QFT and then this one to cancel it out. But it's not very much more. I think probably like 50% more, something like that.
So this is more of like a philosophical question, but so the smallest number of logical qubits you need before these, say, the Jacobi factoring becomes classically intractable is whatever, a few hundred or 600, 800. But then physics becomes hard at like 60 or 70 qubits. So do you have a sort of explanation for that? Like, is it like physics is about using the Hilbert space more densely?
Yeah, exactly. So I mean, my dream is to like push the cost of doing an efficiently verifiable proof of quantumness down to the cost of simulating the circuit, right? That would be the absolute ideal thing. It just turns out that you need probably, it seems, to give some structure to what you're doing in order for the quantum computer to have anything to hold on to, and in particular for the verification for the verifier to have anything to hold on to figure out what's going on. And it seems that at least all of the ways that we've tried so far, adding such structure to make the verification easy also gives new tricks for classically defeating it, right? So it's like, that's the fundamental challenge, is like give enough structure that you can do verification without giving enough structure that it makes it too classically easy. Yeah, this is what Scott and I are always like, the thing we're always fighting against. This is like what you fundamentally want to do that's like a really hard thing to do. But yeah, that's the goal, is like keep pushing this closer and closer to the kind of like simulation limit.
Okay, any more questions? Okay.
I'm curious about elliptic curve
Sure.
cryptography and like
Mhm.
my impression was that the classical algorithms weren't as good and
Yeah.
it's be an opportunity for like a smaller group of quantumness and also like does any of these tricks like
Yeah.
carry over at all or
Indeed, indeed. So I have a few answers to that. So first, these interactive proofs of quantumness that were mentioned earlier, in a paper that I have about those, we introduced a function based on elliptic curves that you can use inside of them. Unfortunately, the gate cost is so much that you like might as well run Shor's algorithm for breaking elliptic curve crypto. It's like not worth it. Indeed, it's true that that since elliptic curve discrete log is harder to break classically, like we don't have to push to as big of sizes. The challenge has been, well, there's two challenges. One, that like factoring circuits have such simpler structure that it's just easier to implement. Like just implementing these factoring algorithms for elliptic curve crypto is just really annoying, which has, I guess, double effects. First of all, it seems like the gate counts end up higher because of all the operations you have to do. I think there's also somewhat of an effect of like, this has literally happened to me. Like you're like, okay, let's figure out a really good implementation of this. And then you like start learning really deeply about how to implement elliptic curve crypto. And you're just like, this is horrible and I don't want to do this anymore. And then you like go have a coffee. So I do think that probably like, I would say part of the reason that we've made factoring so much more efficient is just that like, it's really annoying doing this sort of stuff for elliptic curve crypto. But there have been really good efforts in that. And I do think with like aggressive optimization, maybe it could be pretty good.
I guess just some of the sort of number theory that you use to help you with the factoring algorithms in the quantum setting also like helps you with factoring your classical setting, right? Reasons to kind of try to get.
Yeah.
Right, like the Jacobi symbol, there isn't an equivalent in that, but elliptic curve.
Yeah, exactly. Yeah, and like, definitely a question is whether these tricks I mentioned at the beginning of the talk from like Chevignard, et cetera, can be ported over to the elliptic curve setting, and also, maybe whether they can be ported over to like Regev's algorithm. And once you stare at it for a while, you just kind of are like, well, these tricks are just really well suited for regular factoring. They're just not very well suited for any of these other things we might want to use for them. So it's just like, yeah.
Okay. If there's no more questions, let's thank Greg again for the nice talk. Yeah, let's thank all the speakers of today's session. And that's it for today, except we have a reception waiting outside. Thank you.